Hello, everyone. So last time we were looking at optimization problems, which was an application of finding absolute max and min of a given function. Optimization problems. So if you remember in this type of problem, basically the goal is to maximize or minimize the function on a given interval. So the procedure that we explained, so the process is assign letters, let's say X, Y, etc., to quantities you want to find. And then you have to express the quantity you want to maximize or minimize as a function of one variable only. Say f of x. And then determine the domain for this function. And then find the absolute max or min. Okay, so the quantity you want to maximize or minimize in the level of this course has to be written as a function of one variable, because this is one variable calculus. But in multi-variable calculus in Math 213, you will learn how to maximize or minimize even if you have a function of 2 or 3 variables. So in that course, then you won't have this obligation to write as a function of one variable only. But in this course, according to the methods that we have learned so far, we just know how to maximize or minimize a function of one variable. So even if you have two variables, like the examples we did last time, let's say if you have two variables, x and y, let's say you know that, for example, area is x times y. But if you have if you know the connection between x and y, and you know that y equals to, for example, let's say 5 minus x, then you can substitute y and you write your function as a function of one variable only. Okay, so please do that and write your function as a function of one variable only. And also, you also need to determine the domain, because maximum or minimum of a function depends on the formula, of course, and also depends on the domain. If you don't know the domain, you cannot find maximum or minimum. So determine the domain. Domain means the possible values for x, possible inputs. What are the possible values for your input? If it's a closed finite interval, then it's easy to solve this maximum minimum problem, because we already have a procedure in place for finding absolute max or minimum of a continuous function defined on a closed finite interval, which we explained before. You just need to write down the candidates, like the endpoints and critical points, and then compare the outputs corresponding to the endpoints and the outputs corresponding to the critical points. Okay, and if it's not a closed finite interval, still is okay. You can still maximize or minimize your function. We have also explained a little bit about this and covered some cases. For example, we saw one theorem that was saying that if a function has exactly one relative or one local extremum, if it has exactly one local extremum, and if that local extremum is local minimum, then it has to be absolute minimum. And if that local extremum is local minimum, then it has to be absolute minimum. And if that local extremum is local maximum, then it has to be an absolute maximum. So this was a theorem that we have seen before. We'll see that we'll apply today as well. So we have done some examples last time. Let's continue the examples. This time, let's do this example here. Find and the radius and height of the right circular cylinder, the right circular cylinder of largest volume that can be inscribed in a right circular cone with radius r equals 6 and height h equals 10. Okay, so let me explain about this. We have a right circular cone, a cone here, and we want to inscribe a cylinder inside this cone. So we want to put the cylinder inside this cone. Well, we have different options. There is no unique way to do that. So this is one way to do it, right? So we know that the whole radius, this R, capital R is 6. And we know that this capital H is 10. So that's what we know. But now the way that we want to inscribe the cylinder inside this cone is up to us. We can, for example, inscribe it this way, or we could choose a smaller or bigger radius for our cylinder. So for example, we could go like this. So this one again, let's say this is small r, and this is small h. In this one, small r and small h. And capital R is 6 still, capital H is still 10, right? So when we compare these two cylinders, this one has a smaller R, bigger R and smaller H. This one smaller R, bigger H. So see, it's not obvious how we have to choose our cylinder. Should we go for very small R, much bigger H, or very small R, much bigger very small R, much bigger H, or very big R, much smaller H, or something in between? We have infinitely many choices for choosing our cylinder. Like I said, we could choose very small R, big H, very small H, big R, or something in between. Which one of those will have the largest volume? We want to know about all the options we have to choose our cylinder. Which one has the largest volume? So please remember, the cone is fixed, okay? The cone is fixed, it's given. It's a certain cone, it could be an ice cream cone or any cone, it's given. But we want to inscribe the cylinder inside it that has the volume as large as possible. The question is how to choose the cylinder inside this cone that has the volume, the largest possible volume. Okay. So what is the volume of cone? Volume of cylinder. Volume of cylinder. We know it's pi. Let's denote it with V. And radius of cylinder. Let's denote it with small r. Height of the cylinder. Let's denote it small h. Now volume of cylinder is pi r squared h. Now this is volume in terms of two quantities. R and H. But remember, according to our recipe, we have to write down or express the quantity that we want to maximize or minimize as a function of one variable only. Right now we have V expressed as a function of two variables, R and H. So our next job is to write V as a function of one variable only, either R or H. Now, how can I do that? I can see R and H cannot be unrelated. Once I find the connection between R and H, I can find one of them in terms of the other ones and substitute back, and then I'll have volume in terms of one variable. And there is a connection between R and H here. R and H cannot be unrelated. Why? According to the similar triangles. Look at here. If you look at these triangles here. So to find the connection between R and H, consider the following similar triangles. Which similar triangles? So one of them has radius R. The other one has radius capital R. I mean the side. This is the side of this triangle, smaller one here. See, this is the smaller triangle, this one. And then this is the bigger triangle. So smaller triangle has base small r, bigger triangle has base capital R. Smaller triangle here. A bigger triangle here has height capital H. What about smaller triangle height? How much is it? This height here, but we know that this is small h, this height, and the whole is capital H. So what will be left for the height of small triangle? It will be capital H minus small h, right? This part is small h, the whole is capital H. So this part will be capital H minus small h. Now these triangles are similar, so the ratio of corresponding sides are the same. So by similar triangles, we can say that R over capital R is same as H minus H over capital H. Small r over capital R is same as capital H minus H over capital H. So here I can find, let's say R. R will be R capital H minus H over capital H. So volume will be pi R squared H. This will be pi R H minus H over H squared times H. So this one is pi R squared over H squared. H minus H the whole square times H. Okay, so we wrote V as a function of one variable only. Okay, now we need to determine the domain. So this is a volume V of H basically, right? Because we wrote it as a function of one variable only, and that variable is H. This is V of H. So the function is V, the input is small h. Capital H, remember, is fixed, it's a fixed number. It's the height of the whole cone. Now, what about the input H? What is the domain of H? With domain equals, now small h, look at the height of cylinder. Well, in the most extreme case, small h could be same as capital H. If the small r is very close to 0, right? You can have a very long cylinder with small h same as capital H. In the other most extreme case, you can have a very, so that previous case, we had a very tall cone where small h was almost capital H, or in the other extreme case, you can have a very short cone where small h is almost 0 and small r is same as almost capital R. So in the most extreme cases, small h could be as small as 0 or as big as capital H. Small, because you're not allowed to go outside of the cone, right? So small h cannot be bigger than capital H, and of course cannot be less than 0. So the domain here would be 0 to capital H, because small h is a number which is between 0 and capital H. So we have a function and we have the domain, closed finite interval, so we can easily find maximum and minimum of this function. So we have a continuous function V of H equals pi R squared over H squared times H minus H the whole square times H, defined on a closed finite interval, which is 0 to capital H, and we want to maximize it. So what were the potential candidates? Potential candidates were the endpoints. What are the endpoints? Well, H equals 0 and H equals capital H. And what about the outputs corresponding to this V of 0? Remember the formula for V of H? If small h is 0, this output will be 0. 0 times anything is 0. And if small h is capital H, again, output will be 0. V of capital H is also 0. So of course, maximum will not happen at the endpoints. Minimum happens at the endpoints because the volume is 0 for these two endpoints. And of course, we cannot have volume smaller than 0. So this is the minimum. And now the other candidates are the critical points. So for critical points, I need to set fv prime of h equals 0, derivative respect to h. So I can use the product rule. Well, this is a constant. I can take it out. And then it's product of these two functions. So uv derivative is u prime v plus uv prime. Derivative of h, small h respect to small h is 1. So then I will have pi r squared over h squared times h minus h the whole squared plus derivative of this guy here, h minus h the whole squared. I can use the formula for derivative of u squared. U squared derivative is 2u prime. So 2 times u prime is minus 1 times h minus h. And then this one equals 0. Then we have a pi r squared over h squared, h minus h. Oh, and then times h. This was see uv derivative, u prime v plus uv prime. So this one is uv prime, and this is u prime times v. Okay, and then I can take h minus h also out. What will be left? H minus h minus 2h equals 0. So then I will have either h minus h equals 0 or h minus 3h equals 0. So this one gives me h equals capital H, which we already had it above. And this one gives me h equals h over 3. And then the corresponding outputs, with corresponding outputs, v of capital H, we already saw this is 0, and v of capital H over 3, if small h is capital H over 3, what will be v? V is, this is the formula for v. So pi r squared over h squared times h minus small h is h over capital H over 3. H minus that will be 2h over 3 times h over 3. I just use the formula for v of small h, and small h here is capital H over 3. And then this will be 2v r squared h squared over 9h squared. So this cancels with this, and 2 pi r squared and then this is 2 pi r squared over 9. So lastly, we have to compare the outputs found in 1 and 2 above. And then we have v of 0 equals 0, v of capital H equals 0, and v of capital H over 3, 2 pi r squared over 9. So which one is the smallest? These two, of course, are the smallest, which means absolute mean is h equals 0 and h equals capital H. We have two absolute mean. That's okay. You know, we can have more than one absolute mean or max. And this one obviously is the largest one. And this means that the absolute max is h equals capital H over 3. So the volume, the cylinder with largest volume has height equals capital H over 3, 1/3 of the height of the whole cone. This is the height of this cylinder, and with what is the radius of this cylinder? With radius r. How can I find small r? There was a connection between small r and small h. What was the connection? Let's see here. We can call this formula star. So small r is capital R, h minus h over h. By formula star, capital R, h minus h over h equals R, h minus h over 3 divided by h. So this is 2r over 3. So this cylinder with largest volume has this height, this radius, and the value of the volume for such cylinder is V equals pi r squared h equals pi 2r over 3 to power 2 times h over 3 and I think I made mistake in one mistake in the calculations. So this is pi r squared. Oh, this one is power 2 here. It was pi r squared over h squared. Let's look at the formula for V. Pi r squared over h squared times h minus h the whole squared times small h. H minus h the whole squared. So that will be 2h over 3 the whole squared times h. So I forgot this power 2 here. So then the answer will be 4 pi r squared 4 pi. Okay, let's see whether the screen is freezed. Four pi r squared h cube over 9h squared. And then the answer will be 4 pi. This will be 4 pi r squared capital H. Because h cube over h squared will be h. So this is the rest is okay. So the volume for such cylinder is V equals pi r squared h equals pi 2r over 3 to power 2 times h over 3. That's going to be 4 pi r squared h over 9, which is same answer as what we had above, 4 pi r squared h over 9. That's the volume of largest cylinder, a cylinder with largest volume inscribed in this fixed cone. And absolute max for small h is capital H over 3. Absolute mean is small h equals 0 or small h equals capital H. Absolute mean was not asked here, only absolute max was asked. So the height, we found the height and radius of largest cylinder inscribed, and also the value for volume of such cylinder. The value for volume of such cylinder, once we have small r and small h, we can easily find it, just pi r squared h, and we found the volume. So you have to read the question carefully, see what is it the question asking from you. Does it ask to find the volume of largest cylinder inscribed in this cone, or does it ask for dimensions of largest volume inscribed? If it just asks for dimensions, then we can just say, okay, dimensions are this is small h and this is small r, and that's it. But if the question also asks for the volume, then this is the value of the volume, largest possible volume. So you have to read the question carefully. So in this one, the question was asking about find the radius and height. The radius and height was being asked. The radius and height, we found it here. So if in the exam, if that was the question and you find the radius and height here, you could end your solution here. But just in case, the value of the volume, if it's also asked, is the value of the volume, which we can easily find once we have the value of r and h. Okay, and by the way, the value of capital R and capital H were given in the question. We found it like the general formula for an arbitrary capital H and capital R, but they were given in the question. I think capital R was given as 6 and capital H was given as 10. So in this question, I can also mention capital R is 6, capital H is 10. So then the height and radius of the cylinder with the largest volume is small r or small h. Small h was capital H over 3, right? And a capital H is 10, so 10 over 3. And small r is 2r over 3. So 2 times 6 over 3, which is 4. Okay, so now let's look at the next example. A closed cylindrical can is to hold 1 liter of liquid. How should we choose the height? So 1 liter, by the way, you know that it means 1000 centimeter cube of liquid. How should we choose the height? Choose the height and radius to minimize the amount of material needed to manufacture the can. Okay, so we want to minimize We want to minimize the total area, right? So we have a cone. We don't have one cone there. We want to have we have a fixed volume for our cone. And we can choose the cone whatever the way we want. So we have option, we have control over R and control over H. So this is a very natural problem that can happen, right? So you can buy a drink, for example, inside a can, and the volume is, let's say, 1 liter or half a liter. And of course, the manufacturer wants to minimize the amount of material they want to use and still have the same volume, because they want to, let's say, pour half a liter of some drink inside that can. So the volume is fixed. That's how they want to sell it, in cans of half a liter or quarter of a liter, for example. But of course, they want to minimize the material they want to use. The volume is fixed. They want to use as little as possible for materials. So this is a very natural problem that can happen in any factory. So volume is fixed. So first we have to assign letters to the quantities that we want to find. We want to find the height. So let's denote it with small h. And the radius, let's denote it with small r, such that which quantity will be minimized, such that the total area of the cylinder will minimize. So such that the total area, let's denote it with capital S, will be as small as possible. So what is the next task? Our next task is write the quantity that we want to maximize or minimize, in this case S, as a function of one variable only. So let's write down S, the formula for S first. S, the total area. So this cylinder is a closed can. So it has two circular base, and each circle has radius pi r squared. So 2 pi r squared. And then the side area. The side area is 2 pi RH, according to the formula from geometry. So this is the area of two base. And this one is side area. So we have S as a function of R and H. Now, how can I write S as a function of one variable only? Similar to previous examples. If I can find a connection between R and H, then I can substitute one in terms of the other one, and then substitute back into the formula for S. So what else do I know here? I know that the volume is fixed. So it's supposed to have 1 liter or 1000 centimeter cube of liquid. So volume is fixed. So to find the connection between R and H, use the fact that the volume is fixed. So pi r squared h, that's the volume of a cylinder. This is some fixed number, let's say V0. Again, later we can replace V0 with whatever number we want. In this case is 1000 centimeter cube. But let's again find a general formula for an arbitrary and volume, fixed volume, let's say V0. So then this one easily gives me H in terms of R. H will be V0 over pi R squared. So S will be equal to 2 pi, remember the formula was 2 pi R squared plus 2 pi RH. And then this is going to be 2 pi R squared plus 2 pi R H is V0 over pi R squared. And then this one is 2 pi R squared plus 2 pi pi cancels with pi. So this is going to be 2 V0 over R. This is the formula for S. Now we have to determine the domain. Next, determine the domain. So domain equals, now what domain instead of all inputs? Input here is R. What are the possible values for R? R, of course, must be non-negative. I cannot choose R to be negative. It's the radius of the cylinder. It has to be bigger than or equal to 0 for sure. But there is no maximum value for R, right? Potentially, R could be anything. Of course, because when I choose, remember the volume is fixed. That's right. But even if I choose a very large R, as long as I choose a very small h, I can still have the fixed volume of 1000 centimeter cube. Right? If I choose R as a small number, remember what is the restriction that I want to have? I want to make sure that pi R squared h is 1000, right? Centimeter cube. Now, let's say if R is, for example, 0.1. Still, if I choose h big enough, I can still have pi R squared h equals 1000, right? You can easily solve for h. Let's say if I choose R as a small number, let's say 0.1, then I can have pi times 0.1 squared times h equals 1000 and find h. Or let's say if R is 0.01, still if I choose h big enough, I can still have this. Similarly, if R is very big, let's say if R is 10,000 or 1 million, let's say if R is 1 million, then still that's okay because still I can choose h small enough so that pi R squared h is 1000. Let's say if R is 1 million, then pi times 1 million squared times some number is still 1000, right? Well, just choose that number accordingly so that pi times 1 million squared times that number gives you 1000. So still it is possible. So there is no maximum for R. So although the volume is fixed, I can choose R, even a very, very big number. As long as I choose h small enough, I can still have pi R squared h equals 1000. So there is no maximum for R. So R can go to infinity, and that's still okay. Okay, in the sense that I can still have pi R squared h equals 1000, which is my only restriction here. So the domain here is 0 to infinity because R must be bigger than or equal to 0, and R can be any positive number. We just need to choose h accordingly so that pi R squared h still equals V0. So domain is 0 to infinity. Now we have a continuous function. So let me use open intervals 0 to infinity. Of course, if R is 0, then the volume will be 0. And I will not have volume of 1000 or any fixed V0. So open interval 0 to infinity, any number positive could be potentially okay. So we have a continuous function now. So we have a continuous function, which is S of R equals 2 pi R squared plus V0 over R, defined on an infinite interval zero to infinity. So finding maximum minimum is not as simple as before, because previously we had a continuous function defined in a closed finite interval, but here the interval is not closed and is not finite either. So some people say here this function is not continuous. Well, it's not continuous at 0, but the interval is open interval 0 to infinity. So the function is continuous on this interval. We have a continuous function on this interval. We want to find max and min. What should we do? Well, it's not as simple as previous cases, but still doable, because we said that as long as your function has exactly one local extremum, that local extremum, if it's local mean, it will be absolute mean, and that local extremum, if it's local max, it will be absolute max. So we can say that we hope that we can still find absolute max and mean. In this case, absolute mean, basically, absolute mean, if it exists. Using the methods we learned before. Although the domain is not a closed finite interval. If it was a closed finite interval, everything would have been very straightforward. Although it's not a closed finite interval, we can still hope that to find absolute mean. So let's look at the critical points of S. ds to dr equals 0. That will give me 4 pi r minus v0 over r squared equals 0. Derivative of this function with respect to r, 4 pi r minus v0 over r squared. So that will give me 4 pi r equals v0 over r squared. So 4 pi r cube equals v0. And then r cube equals v0 over 4 pi. R equals cube root v0 over 4 pi. Okay, so we have only one critical point. Well, this gives us the hope that maybe the function has one local extremum, because remember, every local extremum must be a critical point. So we cannot have more than one local extremum, because if we had two local extremum, then we would have at least two critical points. A critical point may not be a local extremum, but every local extremum is a critical point. So if you have one critical point, either we have no local extremum or we have one local extremum. We cannot have more. If you had two local extremum, then we would have two critical points, at least two critical points as well. So since every local extremum is a critical point, we may have no or exactly one local extremum. Local extremum in this case, or in our problem. How can I know? Well, to find out whether a critical point, if this critical point is not a local extremum, then overall we have no local extremum. If this critical point is a local extremum, then overall we have one local extremum. How can we find out? We can either use first derivative test or second derivative test. So to find out, either use the first derivative test or use the second derivative test. So let me use the second derivative test. S double prime will be how much? S double prime will be derivative of this guy, which will be 4 pi plus 2v0 over r cube. So S double prime at the point that we have cube root v0 over 4 pi will be equal to 4 pi plus 2v0 times 4 pi over v0. And the answer will be 8 pi plus 4 pi, 12 pi, which is positive. So if second derivative at the critical point is positive, what does that tell us? That means that that critical point must be a local minimum. So by second derivative test, cube root r equals cube root v0 over 4 pi must be a local minimum. So we have one local extremum, which must be, we had one critical point, and that one critical point turned out to be a local minimum. So overall, remember we said that overall we have either no local extremum or exactly one local extremum. But second derivative test told us that we have actually one local minimum. So overall, what can we conclude? Overall, we have one local extremum which is a local minimum So a theorem we saw last time, theorem from last time tells us that x equal or r equals cube root v0 over 4 pi is the absolute mean of S of R. The theorem was saying that if overall you had one local extremum, exactly one local extremum, and that local extremum is a local minimum, then that local minimum must be the absolute mean. Similar situation for local max and absolute max. So we showed that the total area of this can with the fixed volume V0 will become minimum or will have its minimum value if the value of R is cube root V0 over 4 pi. In our case, V0 equals 1000 centimeter cube. So R equals cube root 1000 over 4 pi, and this is 10 over cube root 4 pi. The radius that the manufacturer must use to minimize the total area. The total area of the can. Remember, the can has a fixed volume, but area could be anything. If we use this radius as our can, then the total area will be minimum. It will be minimized. Okay, guys. Okay, so I think I just realized I made some calculational mistake. One factor, I missed it when I did the calculation here. S equals 2 pi R squared plus, it was 2 V0 over R. I forgot this factor 2. There's factor 2 here. And then the rest of calculation, I should still write that 2. So this will be 2 V0 over R squared. There will be 2 here. And then 4 and 2, they cancel. And I will have 2 here. And when I divide, instead of 4 pi, I will have 2 pi here. And cube root will be 2 pi. And then the derivative test, so this will be a 4 V0 over R cube. But still, of course, it will be positive at this point. This will be 4. And this will be 2. Still positive. And this one we said 2. This one 2. And this one 2 as well. This one 2 and this one 2. Okay, so I just missed the factor of 2 in one of the steps of my calculation. So I just needed to change all the 4 pi's by 2 pi's. Okay, so this is the radius of the can that we're looking for. And the question also asked about the height. It was asking find the height and radius of the can with the smallest material. So this is the radius, and therefore the height of such cylinder will be given by, what was H? It was V0 over pi R squared. So V0 over pi R was cube root V0 over 2 pi. And then this will be, if you simplify, cube root V0 times cube root 4 pi squared divided by pi. So this is cube root V0 over pi times cube root 4. And again, in our case, in our problem, h will be cube root 4 times cube root 1000 over pi. So this is the height of cylinder with volume with volume V0 and the smallest total area, smallest possible total area. Right, so like I said, you have to read the question carefully and see whether the question asks you to find R only or H or both of them, or find R and H and the volume of and the value of the volume that leads that has the smallest possible value. What is it asking? So this is the value of H, this is the value of R, and the value of the volume is fixed here, or the value of the total area. So that one is was not being asked here. But if the question also asks for find the minimum total area of a cylinder with fixed volume, if also asked for the minimum total area, well, you know the formula for the total area. The total area, as we said before, was this one, 2 pi r squared plus 2 pi rh. Once you have the value of R and H, that gives you the cylinder that we are looking for, that has the smallest total area. Once we have the value of R and H, of course, we can substitute and find the minimum value for S as well. Okay, so read the question carefully. Does it ask for R or H or S? But like I said, once you find R and H, you can easily find S. Just make sure that you read the question carefully so that you won't miss any part of any question. Okay, guys.